the last problem on your homework today was kind of similar to this, or really could have been done using this strategy. It was a rate problem. It told you how the pressure was changing over time, it told you how the volume was changing over time, and you found how the temperature changed over time. So these are related rates. A related rate problem has two or more quantities that vary over time and some kind of equation between them. So when we do these derivatives, we had to be a little bit careful on that problem you did. You had like PV equals 0.821t, right? But we did the derivative with respect to time. So when you did that, the derivative of P didn't turn into a 1. It was just P prime. The derivative of V was V prime. Because, just like with implicit differentiation, when we did the derivative of x, it went to 1, but if we were doing the derivative in terms of x, every time we did a y, what did we put with it? dy dx, derivative of y in terms of x. So that's kind of what we're going to do here. We're going to do all of our derivatives in terms of time. So any variable other than time will have a d something dt with it. So our strategy on these problems. A lot of them might be something involving geometry or a picture. So if you can draw a picture, do so. It may not be necessary or relevant all the time, but it can be helpful. Number 2 is super important. You need to record the values of your variables and the rates of change. When I helped people on that problem last week, I made you go out to the side and put v equals this, v prime equals this, p equals this, because there are so many numbers in the problem. So I will have you make a list of all your variables and any values that were given for those. If I don't give you an equation in the problem, we might have to pick one based off our scenario. So the picture might help. You know, if I'm talking about area of a rectangle, what would be my equation? Length times width. If I'm talking about something with a right triangle, what's a common formula we use with right triangles? A squared plus b squared equals c squared. So it's just going to kind of depend on the scenario. Sometimes I might give you an equation of the problem, but if I don't, we have to come up with one that would be relevant. Then we do our derivative with respect to t. So any t's, when you do your derivative, it's just like having an x. Anything else, you have to do implicit differentiation with it. And then number 5, we substitute our values in. How come you can't substitute at the beginning? If you plug in all of your values at the beginning, you have a number. What's the derivative of a constant? 0. And it doesn't tell us what we're looking for at all. The only things you can plug in are constants, values that never change. Anything, any quantity that's changing has to stay as a variable until after we solve the problem. Okay, so that's just the next slide. Reminding you, do not substitute until you have done the derivative. So, let's try a problem. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? I think, did I give you blank slides next to most of these? Okay. Sweet thoughts. Okay, when I'm talking about a rate, it's a derivative. These problems, you can also look at units. They will tell you a lot. When your units are rates, those are derivatives. If I look at my unit, cube, what kind of unit, or when do we use cubes? Volume. So the amount of air in a balloon, does that make sense? That would be our volume. Okay. Since it tells us how it's changing, that's the derivative of volume. So we could put v prime, but I'm going to do dv dt. It means the same thing, it's just notation, but this is a little bit more clear. Derivative of volume in terms of time. The cubic centimeters is my volume, my seconds is my time. It's increasing, so dv dt is 100. If it were decreasing, what would it be? Negative 100. Okay, how fast is the radius increasing? So I want the rate of change of my radius. So dr dt is the thing I'm looking for. When the diameter is 50, what's diameter? So it's saying we have this balloon. The total distance across, is it always the same? No, it's changing because I'm putting air into it, so it's growing, but at some particular point that distance across was 50. You'll notice I don't have any other mention of diameter over here, but I do talk about the radius. If the diameter is 50, what's my radius? 25. So I'm looking for the point when the radius is 25. Alright, if I look at these, I know I need a volume. So what, does anyone know volume of a sphere? That wouldn't be one I would expect you to memorize. I would give it to you. 4/3 pi r cubed is the formula for volume of a sphere. Okay, is the volume or radius constant? No, they're both changing, so I can't plug in anything yet. But if I'm wanting to find a dr dt, we have to do the derivative. So we do implicit differentiation. When we do the derivative of any variable, it just becomes that variable over dt, because we're doing it in terms of time. So derivative of volume would be dv dt. Okay, here the 3 comes down. So 4/3 times 3 would be a 4 pi r, subtract 1 from the power, times, what's the derivative of r? dr dt. If I lost anybody.
So that's the change, because we already have a dv.
So now we can plug in all this stuff. We did our derivative. You can plug in the numbers after your derivative. So dv dt was 100 equals 4 pi, r was 25. So let's look at so to solve for dr dt, we would divide by that. So give us 1 over 25 pi. So we know at that instant, this is how fast the radius is growing. I do want units on these problems. So if we look, that's part of why I make you write it as dr dt. R, what's the unit of R? So divided by is like your per. T, what's the unit for time? Seconds. So if you write it as the dr dt, then your units kind of fill in the blank there. Just the top over the bottom. that x of t and y of t are the x and y coordinates at time t of a point moving around the circle x squared plus y squared equals 25. Differentiate with respect to t. So I just want the derivative of this thing in terms of t. So what would be the derivative of x squared? 2x dx dt, because it's in terms of t, so the implicit differentiation. Plus derivative of y squared. Equals the derivative of 25. Okay, so the next slide is just having you use this. So that's my derivative. And then the next slide, I'm giving you things to plug in. So if my x is 3, dx dt was 12, y is 4, we need to find dy dt. Did I give you anything for units on this? Just kind of explain what's going on in this problem. We had a circle, and you have a point that's just traveling around your circle. So we're looking like when our x value is 3 and our y is 4. If my dx dt is positive 12, that means x is increasing, right? So which way is my point spinning? Is it going that way, or is it going this way? Right. If the x is going to be getting larger, then the point is coming down here. And as it's coming down, what's happening to your y value? Yeah, your y is dropping, so that's why it turned out to be a negative. I want you to take a second, read the next problem, and just see if you can draw a picture. Don't try solving anything yet, just see if you can read it and draw some kind of picture for the situation. So a rocket that is launched vertically is tracked by a radar station located on the ground 3 miles from the launch site. So we have a launch site. And from the launch site, the rocket was going up. Okay, and we have some radar station on the ground. Is the distance between the launch site and the radar station changing? No. So we could go ahead and label that as 3. If it's changing at any point, it has to have a variable. But if it's a constant, we can go ahead and put that constant in. All right. What is the vertical speed of the rocket at the instant that its distance from the radar station is 5 miles and this distance is increasing at a rate of 5,000 miles per hour? Okay, so we're talking about the vertical speed. I don't know the height of my rocket, and it is changing, so I don't know my x. When I talk about the speed of the rocket, that's how fast this is changing. So what variable would that be? Dx dt. The speed is a derivative. That's what we are looking for. At the instant that it's distance from the radar station. So here's the rocket, here's the radar station. So the distance between them would be this. Is that a constant or is it changing? changing, so it needs a variable, so let's call it y. The distance from the rocket to the radar station is 5, so if we're looking at the point when the y is 5, and it's increasing at a rate, so that's how the y is changing. 5,000. Okay, so there's a picture, and there's everything that was given in my problem. You guys have any questions about any labels or drawings? What kind of formula could we use? We would assume this is a right triangle because this is vertical, this was a horizontal distance. So we could do Pythagorean theorem. So x squared plus 3 squared, can I just go ahead and put that as a 9, equals y squared. So now what do we need to do? Derivative. Derivative of x squared would be 2x dx dt. Derivative of 9, 0, so that's gone. Derivative of y squared, I want dx dt. Did I tell you what x is? No. But I need x if I am going to be able to solve for dx dt. I know that the y at this instant is 5 and the dy dt is 5,000. How could I get x? Yeah. We know at the particular instant we are looking at, the y is 5, so couldn't we do Pythagorean theorem to get x at that instant? So x squared plus 3 squared equals 5 squared. So at the instant we are looking for, the x value is 4. So 50,000 divided by 8 is 6,250. Now we need units. It was the x dt. X was my vertical height. What was that distance being measured in? Per, t was time, and in this problem time was measured in hours. Questions on that one? We're going to do one more and then we'll stop for the day. So take a second, read it, see if you can at least draw the picture, and then we'll talk about solving. Ladder 10 feet long rests against a vertical wall. So the wall, the floor, and the ladder. Is the length of the ladder changing? No, so we can go ahead and label that as a 10. So what's happening is the bottom of this ladder is sliding away from the wall. When the bottom comes away from the wall, what's going to happen to the top? Yeah, the top's going down, the bottom's going up. Okay, so the bottom of the ladder slides away from the wall at a rate, so that's a derivative, 1 foot per second. So we need a variable down here because it is changing. It doesn't matter what you call it. If I call that my x, then this is sliding away, so dx dt is 1. If you call it something different, that's fine. That's why the picture is so important. so I know what your variables are. I'm looking for how fast the top of the ladder is sliding down the wall. So I need a variable for this side. If I call it y, what am I looking for then? dy dt. At the instant when the bottom of the ladder is 6 feet from the wall. So the point I'm looking for is when my x is 6. Could you go ahead and find the y that matches up to that instant? We might need it later. We know this would be a right triangle, so x squared plus y squared would equal 10 squared. So at the particular instant we need, the y is 8. So then, Pythagorean theorem, x squared plus y squared equals 10 squared. Again, x and y have to be the variables x and y right now because those are changing. The 10, the length of the ladder does not change, so we go ahead and plug that in. If you want, instead of writing 10 squared, if you want to go ahead and make that 100, that's fine. If we do our derivatives, derivative of x squared would be 2x dx dt plus derivative of y squared would be 2y dy dt equals derivative of 100 so plug in. X is 6, dx dt is 1, y is 8, we don't know dy dt. Why did I get a negative? It's coming down, so we should expect a negative. Okay, units. Y. What are the units on y? Feet per. The time is measured in seconds, so it is dropping 3/4 of a foot every second. Any questions on that? So, this is where I'm stopping today. We have a lot more practice to come, but I do want you to go ahead and try a few on your own. So, you're doing the day 1, 2, 4, and 5.